طيب, hello everybody. So now we are going to discuss this example of the heat exchanger. This is just to give you an idea. If you don't know what a heat exchanger is, it's an equipment that's used to, as its name implies, to exchange heat between two streams. We have a hot stream that we want to cool down and a cold stream that we need to heat. And instead of installing a heater for the cold stream and a cooler for the cold stream for the hot stream, we let the two streams exchange heat. So I'm not spending money on heating or cooling. I am making use of the difference in temperature. So this is a hot stream that I want to cool down. It flows in this blue area inside the equipment, and then this cold stream flows in the pink tubes in this area here. And in this part of the equipment, the two streams are not mixed, but the heat can transfer between the two streams. And then I get a stream that is hotter than the feed here, and a stream that's colder than the feed here. So this is the idea of a heat exchanger. Of course, there are a lot of information about heat exchanger. There are a lot of designs. The design that you see here is one of the very common types, which is the shell and tube heat exchanger. But there are many other types of heat exchangers. But this is the concern of heat transfer courses, so I'm not going to go into more details here. So the information that we know here is that we have a gas stream that is at 500 degrees Celsius, which is this. It's 8 mole percent carbon monoxide, 92 mole percent carbon dioxide. It's sent to heat exchangers and flows across the tubes through which water is flowing. So these tubes, which are the pink areas here, there is water that's flowing, and it enters at 25 degrees Celsius and at 5 bars, and it's fed at a ratio of 0.2 moles of water per mole of hot gas. So each one mole here fed to the exchanger is corresponds to 0.2 moles of water that is fed to the exchanger. And it said that the water is heated to its boiling point and forms saturated steam at 5 bars. So the product here is steam that is saturated at 5 bars. The heat exchanger operates adiabatically. We said adiabatically means that there is no heat losses or gains from the equipment to the outside, or the other way around. So that all the heat lost this is an explanation of the word adiabatically. All the heat lost by the hot gases, and this hot gas is going to lose heat and gets out at lower temperature. This heat lost is gained by the water, which is what we see here as evaporation of the water and rising its temperature to the product temperature. The feed gas flow rate is 1 mole per second, so we know the molar flow rate of the feed, and we need to calculate the temperature. So in this problem, we have two kind of new things that or two points that we need to discuss here in some details. The first here is that each time we know the temperatures and we want to calculate the heat or the work. In this case, we have a different requirement. We are asked to calculate the temperature, which is the first time to calculate or to see, and we will see how we can deal with such a case, which is a very common case that we see. In many cases, we need to know what is the product temperature, and this requires some mathematical manipulation of the equation in order to do this, and we will see this now. The second point, which is a very important point, is that we said before that we are dealing with single phase problems. We haven't dealt with any enthalpy change due to phase change up till now. But what you see here is the water enters at liquid at 25 degrees Celsius and 5 bars, and exits as saturated vapor. So this water is changing its phase. It starts as liquid and ends as vapor. So there is phase change here, and we said we don't deal with, or at this point we deal with single phase systems. So how comes we can deal with this? And we will see how to deal with this. But the steam or the water is, as we said, is a special case, and we were able to deal with water in chapter 7 even without going into all these details that we went through in this chapter. And the reason is we already know the details of water, the information about water. You can go to the steam table and extract the data. And there's a point that we discussed at the beginning of this chapter, that in the cases that we dealt with the steam table, we didn't even care to worry about the changes that happen. We only needed to know what are the conditions at the feed, the conditions at the product, and this is all what we need to do to get the two enthalpies. No matter what happens, change in pressure, change in temperature, change in phase, it doesn't matter. We didn't even worry about this. And this is why we can make use of the steam table. And this again, this makes us feel how great the steam table is, and how useful it is for us, that it saves us all the time that we want to spend on doing these calculations. So this is what we are going to do here. So for first, let's write the equation of energy balance. In this equation is going to be very special here. We have no change in kinetic energy or potential energy, or we will neglect them because we don't have any information about them. There is no work because it's only heat transfer equipment. It's adiabatic, which means that Q equals 0. So if Q equals 0, work equals 0, delta kinetic energy is 0, delta potential energy equals 0, then the only term that's left is that delta H equals 0. And this might be kind of confusing because is this an equation that I can use? And the answer is yes, this is the equation that we're going to use. And this is the actual equation that we use for heat exchangers. There is no exchange of heat between the exchanger and the surrounding, so all the heat lost and gained are already inside the unit. So it's not going to be another Q outside, or a Q term that's outside. So delta H equals 0. We can expand this term now. Delta H is the difference of enthalpy between the product and the feed. So it's going to be summation of enthalpy in minus out, or the other way around, or out minus in, equals 0. The enthalpy in is the enthalpy of streams 1 and 2. The enthalpy out is the enthalpy of stream 3 and 4. So this is what we have here. We know that we can calculate delta H for between 1 and 3. Delta H between 1 and 3, and we can get the data for the delta H between streams 2 and 4. So we will rearrange this equation to be written so that we group the terms for the same components together. So we'll have H1 minus H3 plus H2 minus H4. These are the two terms here, H1 minus H3 plus H2 minus H4. And now I can get the change in enthalpy of water, and this is the change of enthalpy of carbon monoxide and carbon dioxide, which is the gas stream. So in this case, we will calculate these using the integration. We will calculate these or this bracket using the steam tables. There is a very important point here, which is something that we discussed in the previous video, which is about the reference state. So when we calculate H2 minus H4, we are getting data from steam table, and from steam table, as you all know, the reference state is the triple point of water, or the liquid water at its triple point. So it's at almost 0 Celsius and 0 atmosphere, or 0.00116 atmosphere, or something like that. But here we can take the reference state, as we always do, one of the two streams, the feed or the product. So we would better take it as the feed stream temperature. And we will have here two different reference states. And again, this is not a problem as long as we are calculating the two terms, the delta H for two terms at the same reference state. Yani the enthalpy of stream 2 and 4 is calculating using the same reference state. 1 and 3 are calculating using the same reference state. So in this case, this delta H and this delta H can be added without any problems, because delta H is not dependent on the reference state. So you can take any reference state for the two streams that are or the two streams of the same component. So this is a very, very important point. So this is what we have here. We can there's something that's done in the textbook that I think it's very nice, is that you can create a table like this to summarize all the data that we have. So we have columns, one for the substances or the components that we have. We have a column for inlet streams, a column for outlet streams. For the inlet streams, you have the number of moles in one column and the enthalpy in the other. For the outlet streams, we have the number of moles and the enthalpy in the other. And we fill the table with the information that we have. So I have the information about the number of moles of carbon monoxide, for carbon dioxide, for water, and the enthalpies here. I'm taking the, for 1 and 3, I am taking the reference state, the feed conditions. So H1 is going to be 0. I don't know H3, so I'm keeping this with the symbols. And then I have H2 and H4 are not known yet. So what I need to do is to get the unknown terms. So fill the table with these numbers of these symbols here, or the parameters that I don't have values for. So now let's go for the calculation. So for streams 1 and 3, it's going to be as we did before. We will get the CP of the mixture, and from the CP of the mixture we can calculate the delta H. And there is a trick here. In all the cases that we dealt with before, we knew the limits of integration, T1 and T2. Here we know T1 and we don't know T2. So we will do the integration, and then you'd see that the equation is written in terms of T. So this is why the calculation of the temperature would be difficult, because you have T, you have T power 2, you have T power 3, and T power 4. And we don't know how to deal with this up till now. Now for the water stream, we'll go to the steam tables. If you go to the steam tables, we have the enthalpy of stream 4, which is saturated vapor at 5 bars, which is already in the steam table. I'll just go to the steam tables just to take a look at it. So it's at 5 bars. This is saturated vapor. It's 2747.5. So this is the value that we have here. And now we have hydrogen. This is H2, I'm sorry. It's liquid at 25 degrees Celsius and 5 bars. If you go here, of course, 25 degrees Celsius and 5 bars, it's the saturation temperature is 151. So 25 Celsius is liquid, subcooled liquid. So it should be somewhere here. The minimum temperature that we have is 50. So we cannot do interpolation. If we know 0 and 50, we can do interpolation, but I don't know any value below 25, so I cannot do interpolation. So I have one of two options: either to take this value, of course this is given that we have only the steam tables that we have here, is to take this value as the enthalpy, and I'll say that it's only 25 degrees Celsius, so it's not a big deal. So the enthalpy is 209, or we will go back to the or no, we don't need to go back. Or I'm going to we said it's at 5. No, I'm going to go back to the pressure table, and I mean the temperature table. I'm sorry, and say that here I have 25 degrees Celsius, and I'll take the saturated liquid at 25 degrees Celsius as the enthalpy of saturated liquid as the same enthalpy. Why I'm saying this? Because I know that the temperature has more effect on the enthalpy than the pressure. So we are taking this enthalpy here, which is 104.8, to be the enthalpy of water, of the feed, because I know the pressure here is very, very low. It's 0.0317, but I know that the effect of pressure between 0.0317 and 5 bars is going to be minimal. And it's not so significant, so I can take this number as the enthalpy of the water of the feed stream. So this is what we are doing now. I'll check with you later if this is correct or not, but this is what we are going, or how we got this number. I put it as 105. It's 104.8, but I put it as 105. It's almost the same. So now we calculated the change in enthalpy. Of course, this is in kilojoules per kilogram, and don't forget this. So I'm converting this from kilogram to kilomole, and from kilomole to mole, to unify the units to be kilojoules per mole, like here. And we substitute in the energy balance equation. This is the equation that we will have at the end. To solve this equation, we use a method that's called trial and error. This is very common mathematical method that we use to do the calculation of a known parameter in equations like this. They are not simple substitution equation. It's the parameter is available in more than one unit or one term, so you have to do the trial and error. Trial and error means that you substitute with a value, you check the equation if it's valid. And I put any temperature, I know the temperature must be less than 500, I'll put it as 400 for example, and then substitute. If the temperature is 400 is the right answer, then you would see that the right hand side is the left hand side is equal to 0. If it's not right, I try another temperature and keep going until I reach 0. There are a lot of mathematical ways of doing this, and there are a lot of mathematical methods that can be used to do this trial and error. But for now, I'm not going to go into any details of this. But next video, I'm going to show you how to do this using Microsoft Excel. It's a very useful thing that you need to know how to do. But after doing the trials and doing the calculations, you can find the temperature as 299.3, which is almost 300 degrees Celsius. There is one last point I want to discuss here, which is about this H2. Is the assumption that we made a valid assumption or not? So to check this, we have I put here the steam table in the appendix, and this is the value that we got, and this is the actual international steam tables, which is a big book that contains a lot of data about steam. In this steam table, you would see here that there are tables for different pressures. So I have the pressure at 5 bar, and at 5 bars I have the temperature of 25 degrees Celsius. So the enthalpy is 105.3. So the difference between the value that we got and the value that is the actual value, the true value of the enthalpy, is almost less than 0.5 bars, 0.5 kilojoules per kilogram. It's 0.5 out of 105. So it's very negligible difference. And this agrees with what we said before, that the pressure effect is very minimal on the enthalpy. So if you remember, this is the enthalpy of water of saturated water at 25 degrees Celsius. The difference is between pressure here is 0.0317 and the pressure is 5 bar. It's a very big difference in pressure. While 25 degrees Celsius in temperature led to increasing the enthalpy from 105 to 200 and something. So it's 25%. I know it's almost 100% increase. That's why the assumption is valid. Again, the pressure effect is very minimal, and this is a very good example of seeing this. So by this, we are done with this part of the chapter. We only have a couple of things left, which are going to be the effect of phase change and then the psychrometric charts. So we'll start them inshallah next time, or next time I'll start with or do the trial and error, or the solution of the equation, and then we will go for the rest of the chapter. So I'll see you then inshallah. Goodbye.